The Unified Extensible Firmware Interface is a specification that defines a software interface between an operating system and platform firmware. Unified Extensive Firmware Interface replaces the basic input-output system BIOS firmware interface originally present in all IBM PC-compatible personal computers, with most firmware interface implementations providing legacy support for BIOS services. Unified Extensive Firmware Interface can support remote diagnostics and repair of computers, even with no operating system installed. The interface defined by the Extensive Firmware Interface specification includes data tables that contain platform information and boot and runtime services that are available to the operation system loader and operation system. The interface provides several technical advantages over a traditional BIOS system, like ability to use large disks over 2 terabytes and graphical user interface partition table, CPU independent architecture, CPU independent drivers, flexible pre-operation system environment, including network capability, modular design, and backward and forward compatibility. A standard PC BIOS is limited to a 16-bit processor mode and 1 megabyte of addressable memory space, resulting from the design based on the IBM 5150 that used a 16-bit Intel 8088 processor. In comparison, the processor mode in firmware interface environment can be either 32-bit or 64-bit Itanium. 64-bit firmware implementation support long mode, which allows applications in the pre-boot execution environment to use 64-bit addressing to get direct access to all the machine's memory. Firmware interface requires the firmware and operating system loader or kernel to be size matched. For example, a 64-bit firmware interface implementation can load only a 64-bit operating system, bootloader or kernel. After the system transitions from boot devices to runtime services, the operating system kernel takes over. At this point, the kernel can change processor mode if desires, but disbarred usage of the runtime services unless the kernel switches back again. As of version 3.15, the Linux kernel supports 64-bit kernels to be booted on 32-bit firmware interface implementation running on x86-64 processor units, with firmware interface handover support from firmware interface bootloader as the requirement. Firmware interface handover protocol deduplicates the firmware interface initialization code between the kernel and the firmware interface bootloaders, leaving the initialization to be performed only by the Linux kernel's firmware interface boot stub. In addition to the standard PC disk partition scheme that uses a master boot record, firmware interface also works with a new partitioning scheme called graphical user interface partition table, which is free from many of the limitations in master boot record. In particular, the master boot record limits on the nominal side of these partitions up to 4 primary partitions per disk and up to 2 terabytes per disk are relaxed. More specifically, GPT allows for a maximum disk and partition size of 8 Zulu India Bravo bytes. Operation system Linux. Support for GPT and Linux is enabled by turning on the partition config EFI partition during kernel configuration. This option allows Linux to recognize the use GPT disks after the system firmware passes control over the system to Linux. For reverse compatibility, Linux can use GPT disks in BIOS-based system for both data storage and booting, as both GRUB number 2 and Linux are GPT aware. Such a setup is usually referred to BIOS GPT. As GPT incorporates the protected MBR, a BIOS-based computer can boot from a GPT disk using GPT-aware bootloader stored in the protected master boot record bootstrap code area. In the case of GRUB, such a configuration requires a BIOS boot partition. For GRUB to embed a second stage code due to absence of the port MBR gap in GPT partition disks. Commonly 1 megabyte inside this partition globally unique identifier in GPT scheme and is used by GRU only in BIOS GPT setups. From GRUB perspective, no such partition type exists in case of MBR partitioning. This partition is not required if the system is firmware interface based because no embedding of the second stage code is needed in that case. Firmware interface defines two types of services, boot services and runtime services. Boot services are available only while the firmware owns the platform, and they include test and graphical consoles on various devices, and bus, block, and file services. While the operating system is running, they include services such as date and non-volatile RAM access. In addition, the graphics output protocol provides limited runtime services support. See also graphics features section below. The operating system is permitted to directly write to the frame buffer provided by GOP during runtime mode. However, the ability to change video modes is lost after transitioning to runtime services mode until the operation system graphics driver is loaded. Variable services. Firmware interface variables provides a way to store data, in particular non-volatile data, that is shared between platform firmware and operating system or Uefi applications. Variable namespaces are identified by graphic user interface, and variables are key value pairs. For example, variables can be used to keep crash messages in non-volatile RAM after a crash for the operating system to retrieve after a reboot. Time services. Firmware interface provides device-independent time services. Time services include support for time zone and daylight saving fields, which allow the hardware real-time clock to be set to local time or UTC. On machines using PCAT real-time clock, by default, the hardware clock still has to be set to local time for compatibility with BIOS-based Windows. Unless using recent versions and an entry in the Windows registry is set to indicate the use of UTC. The firmware interface specification defines Universal Graphic Adapter Protocol as a way to support device-independent graphics. Firmware interface did not include Universal Graphic Adapter and replaced it with Graphics Output Protocol with the explicit goal of removing VGA hardware dependencies. The two are similar. Most early firmware interface implementations were console-based, but as early as 2007, some implementations featured a graphical user interface. A firmware interface system partition, often abbreviated ESP, is a data storage device partition that is used in computers adhering to the firmware interface specification. Accessed by the firmware interface when the computer is powered up, it stores firmware interface application and the files this application later run, including operating system kernels. Supported partition table schemes include VM, master boot record, and GPT, as well as El Torito volumes on optical disks. For use ESPs, firmware interface defines a specific version of the FAT file system, which is maintained as part of the firmware interface specification and independently from the original FAT specification, encompassing a variant of the FAT32 file system on ESPs and FAT16 and FAT12 file system on removable media. Unlike BIOS, firmware interface does not rely on the boot sector. It defines instead a boot manager as part of the firmware interface specification. When a computer is powered on, the boot manager checks the boot configuration and, based on its settings, loads into memory and then executes the specified operating system loader on operating system kernel. The boot configuration is defined by variables stored in non-volatile memory, including variables that indicate that the files paths to operating system loader and operating system kernels. Booting firmware interface system from GPT partition disk is commonly called GPT booting, despite the fact that firmware interface specification requires master boot record partition tables to be fully supported. Some firmware interface implementations immediately switch to the BIOS-based CSM booting depending on the type of the boot disk partition table, effectively preventing firmware interface booting to be performed from firmware interface system partition on master boot record partition disk. Such a boot scheme is commonly called firmware interface master boot record. It is also common for the boot manager to have a textual user interface so